right, this is day 2 on types of reactions and balancing. We're going to finish redox first. Remember, those are single replacement, single displacement, whatever you want to call it. Now, the first type of example I gave you in the redox reactions was one metal replacing another metal in solution. We talked about when you have an aqueous solution of an ionic compound, that you put that ionic compound in water and it's soluble, it breaks up into its component ions, right? The ions are floating around. Then we throw a metal in there, and if the metal we throw in there is more active than the metal ion, then a replacement will occur. There's similar reactions that go on with metal and an acid. Okay, so before, last week, we talked about a metal plus an aqueous solution. Now we're talking about a metal and an acid. And a metal is still an aqueous solution. But now that you've been through nomenclature and you know how to name acids, how do you know that a compound is an acid when you look at the formula for it? Has an H in front of it, right? So we have some binary acids like HCl or HBr, hydrochloric or hydrobromic acid. We have some ternary acids like sulfuric or nitric acids that we use in lab very commonly. Anytime you put a metal on acid, a metal in acid, it will often react depending on where the metal is in relation to the hydrogen ion on the activity series. If you look at the activity series for metals, hydrogen is the odd fella out there. These are all metals, but if you look at the periodic table, hydrogen is over here, and it's an odd element because sometimes we classify it as a metal, sometimes we classify it as a non-metal. So in this case, hydrogen, we're going to pretend like it's a metal, and we're comparing it to the activity series of all the other metals. So you can see if these are the, these are the most active here, then these are going to be the least active. So if we look at the activity series for metals, so for example, if I looked at the general form for a metal plus an aqueous solution, it would look something like this. A is our metal solid, which remember when we're talking about the charges of an element in its solid form, what's the charge on a metal in elemental form? 0 charge. It has all the electrons it was born with. In general form, we would add it to Bc, which is our aqueous solution. So this would be the metal, and this would be the non-metal in our aqueous solution. If A is more active than B, then a replacement will occur. B would come out as the new solid, and we would have a new aqueous solution, right? That's if it was a metal in an aqueous solution, which is what we already talked about. If we're going to talk now about the general form for a metal plus an acid, it's similar. We're still going to use the activity series as our reference point to determine if the reaction will take place. But now you're going to have a metal solid, just like you did at the beginning. But now you're going to have an acid. And I'm going to put H in front of it, because the H is going to show that I have an acid now. And acids always have the AQ next to it also. So now if metal A is more active than hydrogen, a reaction will occur. And what happens is hydrogen, since it doesn't make a precipitate, what happens here is you're going to see bubbles. In this reaction, you would see, okay, I'm going to put little eyeballs here because remember there's 3 different ways we know to look at chemistry: the macro, the micro, and the symbolic. We're talking symbolic right now. But macroscopically, you would see a precipitate. You would see the hunk of metal. It would start to get a little fuzzy. And I do believe you're doing a single replacement lab next week or the week after where you actually put a bunch of metals in different solutions and you get to see which ones become fuzzy and create the precipitate. In this case, the general form of the metal, what you would get is a gas. Bubbles would be created. So what kind of gas do you suppose would be created from an acid? Hydrogen gas. And what's the formula for hydrogen gas since it's a diatomic molecule as a gas? H2. We're going to put a little G there. So what you would see, and I'll put the little eyeballs here, right? What you would see would be bubbles. So a gas would be produced. So when you see a single replacement reaction in the lab, you're going to take an aqueous solution of some kind, you plunk a metal in it. The metal's going to do one of two things. It's either going to get kind of fuzzy and furry and look like there's junk growing on it, or it's going to start making bubbles. If either of those two things happen, you may have a single replacement reaction going on. The problem is that in double replacement reactions, the visual cues are the exact same. You either see a precipitate or bubbles forming, or in double replacement reactions, the solution can get warmer. So that's a tactile way to tell that the reaction is occurring. All right? So that can be kind of confusing. Then what happens is we get a new aqueous solution with AC. All right? So let's look at an exact example of something like that. So for example, let's see, zinc is a good one, zinc solid metal. If we put zinc with hydrochloric acid, I think that might even be a reaction that you probably do at some point in this class. Zinc and hydrochloric acid. Well, we got to determine if there's going to be a reaction that occurs. Here's our hydrogen. Here's zinc. Who's more active? Is zinc or hydrogen more active? Zinc. So zinc is more active than hydrogen. Will a reaction occur? Yes, it will. What are going to be the products of this chemical reaction? Hydrogen gas. And what else? Zinc chloride. Now, in these, the key is that the charges change in redox. Okay? That's one thing that differentiates redox or single replacement reactions from metathesis or double replacement reactions. Metathesis or double replacement reactions, the charges stay the same. In redox, the charges of the elements change because, remember, electrons are flying around in redox reactions. You got some that are given electrons, some that are taking them. So we have to write new nomenclature for products. And you can't just assume that because it combines 1 to 1 here that it's going to combine 1 to 1 here. What's the charge on a zinc ion if we were going to determine the nomenclature? +2. What's the charge on chloride as an ion? -1. So what should be the correct nomenclature for zinc chloride? ZnCl2. Now, we would put aqueous solution in there. It's not really a new compound that formed. What that means when you see this aqueous solution in your mind's eye, that means what's left in your container is zinc ions floating around and chloride ions floating around. It's not the compound. It's actually, when it says aqueous solution, in your mind's eye, you should think that that's what's left in the solution. It's not making a new thing. So a lot of students are confused about that. Now, we have to balance this equation. How would I balance this thing? I think a 2 there takes care of the hydrogen. It also takes care of the chlorine, so we're good to go there, right? So the equation is balanced, right? All right, let's look at the ionic and net ionic equations for this. So I'm going to rewrite it in landscape version so that you can see where everything is going to and coming from. So we've got zinc plus hydrochloric aqueous solution gives us H2 gas plus zinc chloride in aqueous solution. All right. So that's our balanced equation. To where? Oh, 2HCl. Thank you. Thank you. That would have messed me up, wouldn't it? All right. So now we want to write our ionic equation, which shows symbolically what has happened in the beaker at a microscopic level. Zinc comes down straight away because it's a solid. Now, when we see aqueous solution, remember that means we have ions in solution. It's not a compound. It's a bunch of ions. So if I have hydrochloric and I break it up and I put it into solution, what are the ions that are going to be produced from a single piece of hydrochloric getting thrown into water if it's soluble? I break up HCl, what am I going to get? H plus ions for sure, and what else? Cl minus ions. But if I break up 2 of those pieces, how many of those H plus ions will I get? 2. Now, this is a common error that students make, is they think, oh, H always has to be H2. No, that is when it is a gas. Is it a gas here? No. It is not a gas. It is an aqueous solution. And hydrogen as an ion in solution has a single +1 charge. It is not H2. So you must symbolize it as 2H plus in aqueous solution. Plus, if I break up 2 of those HCl's, how many Cl's am I going to have? 2 of those Cl minuses, also in aqueous solution. And it's super important in your symbolic representation to show the reader that you have solid here, and then 2 things that are floating around as ions in solution. Now, because this is a gas and the ions have come together, we have to keep it as a gas. But because that's an aqueous solution, and as chemists we know aqueous solution, we have ions in solution. If I take one piece of zinc chloride and I break it up, when I throw it into water, what are the pieces that are going to come out of it? I'm going to have a zinc ion. What's the charge of my zinc ion going to be? +2 in aqueous solution. Super crucial to put that notation. Plus, what else am I going to have? And here's where a lot of people go wrong. 2 Cl minus, not Cl2. Chlorine gas. When you hear the words chlorine gas, yes, that's Cl2. But this is not chlorine gas. Is that a gas? No, aqueous solution mean you have ions in solution. So you have 2 of those chloride ions in aqueous solution. All right, now we've got to show the redox half reactions after we eliminate the spectator ions and show the net ionic equation. All right, what are the spectator ions here? Who's just kind of hanging out, watching what's going on? Chloride is a spectator ion, so we can cross those out. So our net ionic equation then is going to be zinc solid plus 2 hydrogen ions in aqueous solution yields H2 as a gas plus zinc ions also in aqueous solution. Now I'm going to show you, and you're not going to have to do this on the first exam, but you will on the second. You will probably also have to do this particular type of equation writing for the lab that you do next week with your lab teacher. So this is an excellent set of notes to save to assist you in that lab as well as to review for the exams. We're going to write the redox half reactions now. That's what this called. And this is a skill that needs to transfer to Chem 152 because in Chem 152 you spend an entire chapter on electrochemistry in which this is a crucial skill for you to have. All right, so zinc is changing and hydrogen is changing. So we're going to write the halves that are now changing. So we're going to write zinc as a solid is changing. I'm going to give some room on each side of the equation to zinc ions in aqueous solution. So there's part of my reaction, the half reaction. The top one, I'm going to put the 2 hydrogen ions in aqueous solution react to form H2 as a gas. So there's the other redox half reaction. I'll wait till you catch up and write that stuff so you can listen to what I have to say. All right, now we've got to decide who was oxidized and who was reduced. So if I look at zinc first, remember, a metal in its solid state has what charge associated with it? 0. It's in solid state. It has all the electrons it was born with. It is not an ion. You find a hunk of zinc on the ground. You have a penny in your pocket made after 1978. The inside of it is solid zinc. The outside is solid copper. A zinc ion in aqueous solution, what did this zinc atom have to do to become this zinc ion and go into aqueous solution? Had to lose 2 electrons. So would I put the 2 electrons that are lost on the reactant side or the product side? The product side, because this is the thing that started out that had all of its pieces. And when it broke up into its component pieces, I have to show what component pieces it broke up into. So that's a good way to differentiate where those electrons go, because that's often a source of confusion for students. Which side do I put the electrons on in the redox half reaction? All right, we're going to do the same thing for the top. Now I like to, these are hard because you have to think about them as hydrogen ions versus hydrogen gas. Here's another thing that you need to put in your memory banks permanently from here on out the rest of your life and in this class. Any of the diatomics as a gas always have a 0 charge, meaning they have all the electrons they're supposed to. There's nothing missing or nothing extra. So, knowing that piece of information, if I think about a single piece of hydrogen ion, one hydrogen ion, what does a single hydrogen ion have to do to become part of this neutrally charged hydrogen gas molecule? It has to gain a single electron. Well, if I have 2 of those pieces of hydrogen, each of which has to gain a single electron, how many electrons should be gained? 2. If 2 electrons have to be gained, where would I put those? On the reactant or the product side? So, a good way to double check if you're writing these redox half reactions correctly is you've got to have electrons on one side being gained versus electrons being lost. All right, remember our mnemonic device? Which one of these is the redox half reaction for the oxidation? Is this the oxidation or is this the reduction? That's the oxidation, because oxidation is the loss. Zinc lost electrons and became an ion. So this is the oxidation half reaction. This must then be the reduction half reaction. I will post this video online. This is going to be an excellent set of notes for you to keep when you're ready to start writing these for your lab in a couple of weeks. All right, so that's single replacement reactions. Once again, to summarize, single replacement reactions, the symbolic, you start with a metal, right, in solid form, and you put something that's in aqueous solution with it. So it either has to be a soluble ionic aqueous solution or an acid, right? You form the new metal plus a new aqueous solution. That's the symbolic part of it. What are you going to see? You're going to see a precipitate, meaning here's your aqueous solution, you put a hunk of metal in there, here's your metal. It's going to start to grow fuzzy on the outside. The color of the solution may change also. Maybe get lighter or darker blue, it may change a little bit, but visually you're going to see it get fuzzy if it is the metal plus an ionic solution. What are you going to see if it is a metal plus an acid? What are you going to see visually? Bubbles. Bubbles are going to come out, okay? And microscopically, what's going on in a redox reaction? If you looked at it microscopically, how could you tell it was redox? What would you see happening between the ion and the metal in the solution? They'd be zipping electrons back and forth between each other, right? Some would be giving electrons away, other ones would be taking electrons. Metals that had neutral charges would go into solution and be ions. Ions that had charges in solution would come out of solutions as metals, right? So there's 3 versions for you. All right, double replacement, also known as metathesis. Reactions have general form. We can say AB is aqueous plus CD is aqueous, and both of these must be soluble. Let's talk about soluble. Before we go on, this is a pretty crucial thing. If you do not know how to use these solubility rules, you will have significant trouble on the next exam. These are the solubility rules from your textbook, Brown-LeMay. I really like these solubility rules. I've given you copies here. I'll post it online so that you can have a copy for yourself. And these are solubility rules that tell you which things will dissolve and dissociate when you put them in water, meaning they're going to break up into their component ions, and which things will not. Remember, in this class, we have a bimodal perspective of solubility. It's either soluble, meaning it breaks up, or it's insoluble and it won't break up. When you get to Chem 152, you have varying degrees of insolubility. You do a whole lot of mathematical calculations with things that are considered insoluble in here. So don't be confused when you get to 152 and you go, hey, I thought that stuff was insoluble. Yes, because that's in here. We talk about it only as bimodal, either soluble or insoluble. So that's what this is telling us. Soluble things, insoluble things. That means when these are put in water, they will dissociate. Meaning they're going to come apart and form ions in solution. If they're insoluble, these will not dissociate when placed in water. So it just depends. So let's practice using them. Think about what it is that they mean. All right, soluble. The way that they list these compounds is based on the anions. Some of them are monatomic anions, like chlorine, bromine, and iodine. Some of them are polyatomic anions, like nitrate, acetate, and sulfate. And that's because it's easier to reference them as chemists based on the anions and what things they will be soluble with. So you look at the anions and then you think, okay, what positively charged particles, if they are connected to them, will they dissociate from when you put them in water? So nitrate is one of those that we call infinitely soluble. There is nothing it won't dissociate from. Nitrate is infinitely soluble. Anything it's hooked up to, when you put nitrate and anything in water, it always dissociates. Same thing with acetate. Acetate is one of those that always, when you put it in water, it's always going to dissociate. So, for example, we had some things like lead nitrate or sodium nitrate. If I put either of those in water, they always break apart. Anything hooked up to nitrate always breaks apart. There's something that you use a lot of in Chem 152. Does anybody know the name of this stuff? Acetic acid, also known as vinegar. Common name for acetic acid is vinegar. You spend a lot of time talking about acetic acid in Chem 152, but that's not what we're talking about here. We want to talk about acetate. Well, that does have acetate in it. That's why I was using it. So acetic acid is slightly soluble, but if we took at something that we're looking at a metal, like sodium acetate, there's acetate. We know, yes, that would always be soluble under all conditions. Anything hooked up to acetate, you plunk it in water, it's going to break up into its component ions, all right? Now we get to the ones that have a few exceptions. These are things that are generally soluble. So, where are chlorine, bromine, and iodine? This is going to help you remember these rules. Where are chlorine, bromine, and iodine on the periodic table? Right here, they're halogens. They're members of the same family. So because families act together chemically and physically, they all follow the same rules. They're soluble with everything unless the thing that they're hooked up to is silver, mercury, or lead. So if I have something like silver acetate, or silver chloride, AgCl, is that going to be soluble or insoluble? Well, chlorine is generally soluble, but what about when it's hooked to silver? No, so we would say that's a solid. It would not be soluble. How about sodium chloride?
Yes.
Chloride, it's not silver, mercury, or lead. It's sodium, so is that soluble? Yes, it is. How about cesium chloride? CsCl2. Chloride is generally soluble except when it's around silver, mercury, or lead. Is cesium chloride going to be soluble? Yes, it is. When I put it in water, it would make an aqueous solution. So see how that works? All right. so they're kind of picky. The only one that's a little bit different in the soluble things is sulfate, because these are all very similar. The halogens are very similar. Sulfate is soluble with everything except for strontium, barium, mercury, and lead. All right? Things that are insoluble, meaning it doesn't matter what it's hooked up to, it will never dissociate. Sulfide is one of those that's always insoluble. So say, for example, I had sodium sulfide, NaS. Let's see, Na would be +1, S is -2, so it would be Na2S. Would that be soluble based on our rules here? S is generally insoluble, except if it's hooked up with ammonium, calcium, strontium, or barium. So is this stuff, NaS, going to be soluble or insoluble? These are things that are insoluble. Now the exceptions make them soluble. Okay, so this is a bimodal chart. You have to think about this bimodally. So these are things that are generally insoluble. Sodium sulfide is anything with sulfide is generally insoluble. The only thing that would make it soluble is if it's ammonium, calcium, strontium, or barium. So is this soluble or insoluble? Insoluble, yes.
It also says the alkali metal cations on there. So wouldn't it be insoluble?
Thank you. So if we look at the periodic table, let me get a periodic table here. Where's sodium? Alkali metal cation. Very good. So this is actually soluble. How about calcium sulfide? Would calcium sulfide be soluble based on these rules? Yes, it would. So would I put AQ or solid? AQ next to it when it's in water. How about cobalt? Let's see if it was a +3 sulfide. Would that be soluble or insoluble? It's not one of the listings. Generally, that means it's going to be insoluble. All right, practice will help a lot in using this. This is what you're going to reference for double replacement reactions when you're going through. Now, if you look at these, take out this handout real quick. The types of reactions, the reading on the types of reactions, where is that? Here we go. All right. Let's look at this really quick. Okay, so these probably should be called single replacement. Your reference here is going to be the activity series, right? And that's because single replacement reactions, it's the activity series that determines if the reaction will take place. So your reference to determine if it will take place is the activity series. Double replacement, your reference is going to be the solubility rules. You'll see what I mean in just a minute. So, as you're doing each of these, and I believe you have a lab next week on a single replacement and the week after on solubility rules, both of these references and the information that I'm giving you now in the notes is going to be uber helpful when you're going through and writing the reactions that you need to for lab. All right. So those things have to be soluble. When you're starting out with a double replacement reaction, it's different than single replacement. Single replacement, remember, you got an aqueous solution and a metal. Now you have two aqueous solutions. So visually what you're going to see is you're going to see two containers, and they're going to be clear, meaning they're going to be transparent. They may have a color to them. They may be blue or yellow or some color, but they're going to be transparent. You're not going to see any particles or any solid stuff in them. All right? So that's what you would see. It would look like a clear colored solution, maybe lemonade and clear water. Or maybe coffee and lemonade would be a good example. You can see through them, but there's not going to be any particulates in them. Then when you put them together, what happens is particles trade places. In this solution, I would have A ions and B ions floating around, right? And A ions, since they're first, are always the positively charged particle. B ions, since they're listed second, are always the negatively charged particle. Same thing here, that's the positive, that's the negative particle. So in this solution, I would have C ions and D ions floating around. So this is the micro microscopic perspective of the symbolic version that I'm showing you now. I want you to think about both things, all right? So we've got the symbolic version. So now if I take this and I pour everything together, right? I'm going to add this solution and this solution together. So now what I'm going to have is I'm going to have one big solution party, and I'm going to have A and B and C and D floating around there. Question?
Would that be a mixture or a compound?
It would be a mixture when we first add them together, but once the chemical reaction takes place, then you would be forming a new compound if you see a precipitate. Good question. Good question. These initially would be solutions, which would be homogeneous mixtures, but depending on if you had a chemical reaction, that would certainly change. All right, so you look at this, and then what happens is, would A and B recombine? Remember what we said about A and B? Would they recombine? No, because they're soluble. They don't like each other enough. They like water better. Would C and D recombine? No, because they're soluble. If you see a precipitate, so what you're going to see in this kind of chemical reaction is one of two things. You're either going to see a precipitate, which is the first kind of double replacement we're going to talk about today. The second kind, you would see the bubbles. The precipitate you would see would be something recombining to form a brand new compound that is insoluble, meaning that a plus and a minus liked each other so much that they ignored that hydration ring of water we talked about last week, and they came together and they pushed the water aside, and a new compound was formed. So who could have hooked up? Would A and C hook up? No. Why not? They're both positive. Would B and D hook up? No, they're both negative. So maybe A and D might have hooked up. And you always put the A first, because that's the positive ion, and the negative ion second when you're writing the new formulas for products. The second thing you would always put is the second compound. C would go first because that's the positive ion in the new product, and B would be the second compound. So you always must put the positive ion first, the negative ion second. Now one of these will be insoluble. And that's the thing that is the precipitate. The thing that is insoluble is the thing that formed the precipitate. So one will have an S and the other will have an AQ because that's the precipitate. Chemists abbreviate precipitate PPT, so that's the thing that is the precipitate. What you would see is in our new container, all of a sudden you get it would first get cloudy. When you put them together, it would become very cloudy, the solution. And if you allow the solution to settle over time, there would be a precipitate that would settle at the bottom of it. It would be a solid, that's the precipitate, and above it, it would be another clear solution. Now, it may be colored. It may still have a color to it. It may still be blue or yellow or some color, but it would eventually become clear, and the precipitate would settle to the bottom. All right, so let's look at a real-world example of what you might see that happening with. Here's a very famous reaction that's often on the cover of chemistry books because it is a really good example of a double replacement reaction. All right, potassium iodide and lead 2 nitrate coming together. Let's check out our solubility rules. Make sure they're soluble. Potassium iodide, we're going to practice here. What would I look up to determine if potassium iodide is in fact soluble? How would I use my solubility rules? Iodide. So I look at iodide, that's generally soluble. So I go, okay, that's a good sign. It's probably soluble, but let me double check. If it's iodide, is that silver, mercury, or lead? No, it's not. So what could we deduce about potassium iodide? Is it going to be soluble? Yes, it would. So in your mind's eye, there's the symbolic version. I want you to think, oh, I would have potassium ions and iodide ions floating around in the beaker of potassium iodide that I have here. All right, I'm going to add to another sample, my lead nitrate. Well, I don't even have to look up my solubility rules because I know nitrate is always soluble, right? So what could I say about this stuff? What kind of ions would be in there? Lead ions. What would the charge of the lead ions be? how many positives? 2. And how many nitrate polyatomic ions would be in my beaker? 2 of them, right? Because it's PbNO32. Once again, I'm helping you out in Chem 152 when you all get there. All right, now I'm going to have a big, giant ion party. I got my potassium in there, I got my iron, I got lead floating around, and nitrate attended the party as well. Who might hook up? Potassium and nitrate might be liking each other pretty much to hook up. Who else? Lead and iodine. Once again, you've got to write new nomenclature for products, but your job with double replacement reactions and products is easier because the charges stay the same. So whatever the charges are as reactants, those charges stay exactly the same as products. So if that's the case, is that the correct nomenclature for potassium nitrate?
Yeah.
Yes, it is. It's a 1-to-1 relationship because they both have a +1, -1 charge. If I want to write the formula for the second potential product, which in this case is going to be lead iodide, what would be correct nomenclature for lead iodide? PbI2. Now we have to determine who is aqueous and who is the solid. Who was the one that came together? Well, right off the bat, I'm pretty confident that this was not the precipitate I saw. And why do I know that? Nitrate is always soluble. So what symbol am I going to put next to it? AQ. So to me, I think that's probably not the precipitate, but let's double check. I'm going to look up iodine. Is that silver, mercury, or lead? Yes, it is. So that is not soluble. So what symbol would I put next to it? S. There's the culprit. There's the precipitator. Those are the ones that hooked up at the ion party, right? All right, how would we balance this thing? 2 KIs. Then what? I think we need 2 there too, don't we? Yep. Right? Okay, here's a way to think of it. Remember we talked about solubility rules as looking at who's going to dissolve in water and who's not? I also want you to think about solubility rules as if you go to a party. And I know all you college students go to lots of parties. And I want you to think about who would precipitate at that party, right? Now a lot of people call this a participate. No, it is a precipitate. You must participate in the chemical reaction in order to form a precipitate. But it is not a participate, it is a precipitate. So if these ions precipitate, that means they come together in the solution. They saw each other across the crowded beaker, and they decided, whoa. Clouds parted, the sunbeams came down, the angels started singing, and they go, iodine, my beloved, lead is over here and really wants to meet you. And they went home and they precipitated and formed a new ion. So these, here we go, these are the players. These are ones you have to be suspicious of that are going to precipitate. Boy, oh boy, I'll tell you that carbonate. You see carbonate in there? They're big precipitators. You always got to be suspicious of carbonate precipitating something in your solution. Phosphate and hydroxide. You see those? You go up. I'm suspicious. There's phosphate. I bet those are the precipitators. We're not done. Don't put your stuff away. You still pay for 2 minutes of my time. We're not done. Let's do the ionic and net ionic equations. I don't want to do this tomorrow because you'll forget, or Tuesday. So we got 2 KIs plus lead nitrate gives us 2 potassium nitrates plus PbI2. Important that that's solid and aqueous because that's going to determine how we write our net ionic equation. I'm going to do it pretty quick because I got 1 minute. There's my balanced equation. Here's my ionic. I would have 2 potassium ions in aqueous solution when I break up 2 pieces of potassium iodide. I would also have 2 iodide ions, also in aqueous solution when I break up 2 pieces of potassium iodide. I would have how many pieces of lead in that? 1 piece of lead, it would have a +2 charge. How many nitrates would I have? 2. Which would yield, is that since that's aqueous solution, I'm going to make sure that I put them as ions. I would have 2 potassium ions in aqueous solution plus 2 nitrate ions, also in aqueous solution. And then since that's the solid and that's the new compound that came together, I have to show symbolically what went on at a microscopic level, and I keep that together as the solid. I do not break it up and show that it is ions in solution. Now, in double replacement reactions, you have 2 spectator ions. What are the spectator ions here? Who is the exact same on both sides? Looks like potassium's exactly the same. What else? Nitrate's exactly the same. Now we write our net ionic equation, which shows in my solution I had 2 iodine ions that were lonely iodide ions before they came to that party. Once they came to that party, they looked at lead across the crowded beaker, and they decided to precipitate. They said, ooh, baby, we're going to form a new compound. And there's your net ionic equation. All right, and a silly story to help you remember. You ready for a quiz on